Hey guys, this is Chrissy, and I'm going to try to do some Chapter 19 examples. This is from the recitation copy that I posted on D2L for Chapter 19. These are in no particular order. 19-103. Assuming a pupil diameter of 3 millimeters, what is the angular resolution of the human eye for light in the middle of the visible spectrum? So at about 550 nanometers. I gave you the answer of 0.01 degrees. Let's take a second and remember what angular resolution is. When we have, let's say that this is our eye. We have one star here and one star here. We have the angular like an angular size. So we have light coming from there to your eye and light coming from here to your eye. The angular size of that we say is theta. The closer these stars are, the larger the angular size. The farther they are, the smaller the angular size. I'm stating as a fact that every optical device has a limit on the angular resolution that it has. It can only differentiate things that are so far away. The way that we find if we can see something clearly is by finding its angular resolution. So your eye can only identify, this angle has to be a certain size for your eye to be able to identify this as two different stars instead of just as one kind of blob of star. So any angle that's, if this is, let's say that this is our minimum angle that we can resolve. And we know that it's 0.01 because I gave you that. So what that's saying is if these stars are separated by an angle of more than 0.01 degrees, we'll be able to see two different stars. If they're separated by less than 0.01 degrees, we'll kind of just see one blob of generic brightness. That is the angular resolution that we're looking for. So now let's start doing it with math. Remember, we don't actually know this. I just gave that to you so you could be working towards it. The equation that we have from the notes is, I think it's on page 5 in the Chapter 19 notes, so the last page. We have theta 1. Theta 1 is our minimum angle that we can resolve. Theta 1 equals 1.22. That's just a number that is a constant here. Times theta over d. Times lambda over d. Lambda is the wavelength, and d is the diameter of the thing that we're looking at. So in this case, it's the diameter of your eye. So we say that's equal to 1.22 times 550 10 to the minus 9 meters over 0.003 meters, 3 millimeters, and that is our lambda. We get theta to be 2.24 times 10 to the minus 4. You'll notice that that number is not that number. But we didn't actually do anything wrong. What it is when we're solving for just a theta on this side, this theta is going to be in radians. So theta is equal to 2.24 10 to the minus 4 rads. I find it easier to think in degrees, so let's convert that. It wouldn't be wrong if you said it like this, so that wouldn't be a wrong answer, but let's just get it to degrees for completeness. So the way that you go from rads to degrees 2.24 10 to the minus 4 rads. You multiply that by 180 over pi. Another thing that you might see is 360 over 2 pi. That's the same thing. Do that math, and you get theta 1 equals 0.01 degrees. That is a good estimate for the angular resolution of a human eye. Now we take a look at a microscope. The objective lens of a microscope has a focal length of 2.4 millimeters, and the eyepiece has an angular magnification of 15. The object is positioned 0.06 millimeters beyond the focal point of the objective. The focal point of the eyepiece is positioned at the real image formed by the objective. The near point of the user is 25 centimeters. What is the magnitude of the overall magnification? There are a lot of words here. Let's break them down. First, let's draw a picture of what we have. What we have is let's draw that a little lower. We have our objective lens, and we have our eyepiece. We have a focal point of so we have FO, FO, and then we have FE, FE. So we have our lenses and we have our focal points. They gave us that FO, the focal point of the objective, is equal to 2.4 millimeters. Also that ME, the magnification of the eyepiece, is 15. We also have our object position. It tells us that the object is located 0.06 millimeters beyond the focal point of the objective. So just beyond that focal point, we have our object. So that would be, we're going to use the notation from before. So we say that S, our object position, is equal to FO plus 0.06 millimeters. First, we'll start with our thin lens equation. Our thin lens equation is 1 over S plus 1 over S prime equals 1 over F. In this case, it's F of the objective. Our S is going to be 1 over 2.4 millimeters plus 0.06 millimeters. That's our S, which comes out to just adding those two, 2.46 millimeters. That's our S. Plus 1 over S prime, we're looking for that, equals 1 over 2.4 millimeters. Rearrange that, and we get 1 over S prime is equal to 1 over 2.4 millimeters minus 1 over 2.46 millimeters. 1 over S prime is going to equal 25 over 246, giving us an S prime of 98.4 millimeters. What this is saying, so we can label that 89.4. So that is our image position. And it told us that the focal point of the eyepiece is positioned at the image formed by the objective. So the image that was formed is going to be at the focal point of the eyepiece. We get that. That we can say this here, 98.4 millimeters. Now we can move on to finding the magnification. We're looking for the overall magnification M. That is M equals MO ME. ME is 15. We know that from up here. But we need to find MO. MO is equal to minus L over FO. That's from the notes. I don't know if I stated this in the notes, but we have this thing called, we have this L. L is the tube length. This is the distance between the objective lens and the focal point of the eyepiece. That is L. L in a microscope is the distance between the objective lens and the focal point of the eyepiece. That's how we are defining L. In this case, we were given that the image is located at FE. So where here this is S prime, this 98.4, that S prime is also L. We can say that our magnification is negative 98.5 over 2.4. We get MO to be minus 41. Our magnification of the objective is minus 41. It's 41 times larger and it's inverted. Plug that into our equation here. M equals MO ME equals minus 41 times 15. Our final magnification is minus 615. It was just asking for the magnitude though, so we can say that the absolute value of the magnification is 615. That is a microscope.